Sorry, did I take your hands off? I can't.
Yeah, sorry.
It's all right. Well, first of all, I think it's awesome that there's so many people here. I thought a lot of people would be not coming into the office today because it's a 5-day weekend for some people, but thank you everyone for trekking out. Today we've got 2 talks. First is on BigQuery. I think it's our first GCP talk. Second talk. Matt and Leah are going to give us an introduction on geospatial data, I assume, and machine learning. And then I want to say a big thank you to Adrian for volunteering a few hours before this event actually started because Lizzle from Microsoft unfortunately got sick. So wherever Adrian is, thank you for volunteering at the last moment. He had a talk up his sleeve. Also, a big thanks to Core Innovation Hub and Google for sponsoring the event tonight and also the beers and pizzas that we're all enjoying. Standard slide we always add in. We're always looking for speakers. I think we've got speakers lined up for the rest of the year, but as we've learned today, sometimes it's good to have speakers, in our back pocket that we can ask and talk. So please reach out to John or myself if you want to speak at any of the events. As I always say, you don't need to have a big idea, just any small problem you've solved at work. Most people here will be happy to hear about it. I've already said that. Okay, that's all from me. Without further ado, I'll hand it over to Matt and Leah. Yeah, I'll get rid of my laptop.
Switch over. Okay. Okay. Can you hear me without the microphone? In fact, no, we've got a live stream, so I've got to use the microphone. I'm usually loud enough, but
Just give it a pull.
Just let me know. Okay. Yeah, thank you very much for coming tonight. I know day off tomorrow, so I wasn't expecting to see many people in here, but I'm guessing some of you got Friday off as well. Today, you've got myself, Matt Turner, so I work as a principal architect for Google Cloud. I've been here just over 4 years. Previous life was 25 plus years in Oracle world. Very different beast, Google from Oracle. And I've got with me, we're lucky enough to have Leah Kaplan. Leah's our lead for GeoSpatial for APAC. So anything that you need to know about GeoSpatial, Leah's the person to speak with. Excuse me. So what is BigQuery? So before I go into that, I've got a quiz. Anybody like to have a guess what these 3 things have in common? Anybody want to give me the names of those 3 objects? There's a prize in it. Shout out. On the left-hand side.
Is the prize chocolate?
No, no chocolate, sorry. On the left-hand side, I'll give you a clue, you've got Colossus on the left-hand side, okay? Come on, everyone knows what's on the right-hand side here. Borg, correct, Borg.
Yeah.
And in the middle, we've got Jupiter. Now, anybody hazard a guess of what those 3 have in common?
Out
What was that?
outside of what?
Okay, anyone else? Okay. These 3 things are the infrastructure that powers Google. Colossus, Jupiter, and Borg. Oh, whoops, too far. Now let me just explain that a little bit. Google was formed in 1998, 2 guys in a house in Menlo Park in California. The problem they set themselves was, how do we scrape all the data from the internet? How do we transform that data into something useful? And how do we put a nice little user interface on it so our customers can find what they want? Now, obviously, with a challenge like that, they couldn't just go and get an Oracle or a SQL Server database off the shelf to store the data in. They needed to think differently. Part of the work they did was actually create white papers. And the first 2 significant white papers came out in early 2000. One was around MapReduce, and the other was around Google File System, which became HDFS. But they those white papers were really the foundations of what became, we call the big data stack version 1. So with your cloud eras, etc., etc. Now, the fundamental issue with this infrastructure was storage and compute were tightly bound. You wanted to increase the storage, you had to create another node, and the compute came along for the ride. Very similar to anyone Teradata users here? Any Exadata users here? It's quite similar in terms of if you want more storage, you need to bring the compute along for the ride. Google decided very quickly that this would not be cost effective. So the decision was made to actually look at, firstly, commoditizing the hardware. So everything that's run on Google is run on commodity hardware with everything stripped back. There's nothing on the hardware that isn't actually needed for the day-to-day running. And leveraging the power of parallelism. So everything in Google is tightly bound and massively parallel. Now, that led to creation of a second generation of file system, which is Colossus. Colossus powers all the services that you see with Google, whether it be Gmail, whether it be Photos, whether it be leveraging Google Maps. All of it is powered by Colossus. And on this side, Borg is actually the compute power. So Borg is, if you think about it, modern stack Kubernetes for those of you that are developers. And that became very important with respect to leveraging containers and being able to scale around the world and provide the compute where it was needed. Now, obviously, when you've got compute on one side and you've got compute on one side, storage on the other side, what you need in between is a massively scalable and very quick network. And that's what Jupyter is. So Jupyter is a petabit bisectional network, which means that every service connects to every other service, delivering a petabit per second bandwidth. And the reason for that is obviously with the world of cloud, all your services are naturally joined together. It's not like the old world when you may have had a 3-tier middleware stack, which your web browser request went down into the application, went down into HTTP server, hit the application server, hit the database, and then went back up and returned the data very north-south. With the modern network infrastructure, there is need to be more than that. So why am I telling you all this? Because I don't know if you're like me, but infrastructure sends me to sleep a little bit. The reason I'm telling you this is because Google's BigQuery is built on top of this bare metal infrastructure. Now, why is that differentiated? There is no other cloud provider that can scale their data warehouse like we can. We've got, and I'll talk a little bit more about it, we've got customers now that are into the hundreds of petabytes of data in production, trillions of rows of records in a single table, and it's completely serverless. So you don't have to worry about the infrastructure. You just bring your data and start to use it. There we go. So just an idea of scale. As I said before, we've got one customer's got 350 petabytes of data. How many millions is that? 100 trillion rows queried, over 10,000 concurrent requests. So the scale of this thing is pretty impressive. Obviously, the more you use it, the more you pay for it. So we do have pricing models that are based on ad hoc usage and a usage that is more consistent. So you might buy a bulk of compute to actually run your everyday workloads. I don't want to talk too much about costs today. Whoa, go back. Sorry, my clicker's not working particularly well. Maybe I step over here. Okay, so on the right side there, you get an idea of the architecture. As I've mentioned before, you've got your distributed storage with 10 nines of durability. You've got your high available compute cluster. We actually base it on open source Dremel, and it leverages Borg under the hood. And then you've got this distributed memory shuffle tier that does all the processing of the data and keeps the data fresh and the structures all up to date, which is part of the file system that is used. Now, in terms of the capabilities, as you'd expect, you've got all the traditional enterprise goodness, identity management, security. We secure, we encrypt by default at rest and in transit. I've mentioned already the petabit hardware, petabit network, and the hardware infrastructure. Now, as I said, we are completely elastic. So if you've got data set, which is absolutely massive, you don't have to pick a t-shirt size of infrastructure to say, well, I think my data might be here today, but I think we might grow to this. So how do I size it? You don't bother about that. Just bring your data. And in terms of the storage costs, absolutely cheap as chips. Okay, that's a northern phrase for any northerners in the building. So the storage costs are really cheap because we don't have to bring the compute along as well. So if you're talking about wanting to take smart meter readings, for example, had a customer last week who wanted to increase the frequency of their sampling of the smart meters from hourly to every 5 minutes. Not a problem. We can handle that volume. We can handle that velocity, and we can do it at low cost. So if you're doing anything in the OT space, for those of you that are in mining or oil and gas, any of the other industrial areas, then seriously, if you want to future-proof yourself, have a look at BigQuery, because as I said before, nothing scales like this does. A bit further about the functionality, we handle all types of data. So whether that be your structured data, your JSON data, any unstructured Parquet, whatever those formats are, you can either leave it as external data files and reference them as external tables, or you can import them. When you import them, you can optionally bring them in as structured tables, so you can actually completely replicate the JSON structure in the table itself, and then you can unnest the data in queries. So that's built in by default. And as I said, we do support GeoSpatial. So any post-GIS users, any GeoSpatial users in the room? So we support all the standard geo formats, point, polygon, line string, etc., etc. And Leah will go a little bit more into that. Streaming, we have a streaming API. So you can stream the data in. As that data is being streamed in, you can read it. You can actually start reporting on it as it's coming in. Okay, that's fairly unique. I believe others have slight delays. We don't. Ours is up to the second in terms of that. And the beauty of this is as well, if you've got materialized views on top of your data, I come from an Oracle world. Whenever you updated the base table, your materialized views were rendered stale, and you had to go about refreshing them. In BigQuery, all materialized views are kept up to date, and you don't have to go manually refresh them. So that's another good feature in there. One final thing, Analytics Hub, we've just released. It's a way of actually sharing data both internally, externally in your organization. You create an analytics exchange. You create the metadata around that exchange. You publish it, and it appears as a like a traditional shopping cart where your customers can search for the data, request access to the data, and then start consuming that data. I think I've already, final thing, BigQuery Omni. So not only are we saying, come and you query your data that exists in Google Cloud platform, also you can query your data that's in an S3 bucket or in Azure storage as well. We are able to deploy that capability into those clouds, use BigQuery itself as a central control plane. You'll see the data set and you can query it transparently, and it'll automatically push the query down to the cloud where the data set resides and return the result set. So if you're looking at challenges with egress costs or pulling out large volumes of data, typically in an analytics query, you're only ever really returning subsets of the data that can be highly aggregated. So you can leverage something like BigQuery Omni to do that and reduce costs and reduce time to value. Okay, very brief overview. I'll hand you into Leah now, who will take this forward.
I'm not a walker, I'm sorry. There we go. All right, can everybody hear me? We good? Okay, I'm gonna just have to use the clicker also. So hi, my name is Leah. Thank you all for joining us. Thanks for having me. This is
closer. Sorry.
closer. Is that better?
Can everyone hear that?
Yeah, we're good? Okay. This is going to be a really, really quick overview of GeoSpatial. Maybe I can come back next year and talk some more if there's more interest. All right. So if you work in the geospatial field, you know that until very recently, the tools that we had were desktop tools. So our workloads tended to be constrained by what you had available, your local GPUs, your local disk size, you name it. But one of our missions at Google is to, bring cloud scale to any workload. And we love geospatial. We don't do a good job of talking about it, unfortunately, which is one of the reasons that I'm here today. But our vision is to release all of your workloads with Google Cloud Scale. That's not good. Oh, there we go. Sorry. So when we talk about geospatial at Google, we actually have 3 highly differentiated products. We've got BigQuery, which Matt gave you an overview on. We've got Earth Engine, which I'm going to sneak in there, even though it's not BigQuery, just a little bit, and Google Maps Platform. So I'm not going to talk much about Google Maps Platform. I think everybody's actually probably familiar. I have no sense of direction. I don't go anywhere without Google Maps. Most people know Google Maps. There's actually a commercial version that you can use as well. But let's start by talking about BigQuery and Earth Engine. So at a very high level, when we talk about geospatial data, there's really 2 types of data that we're talking about. There's tabular data, so your stock standard, anything that would fit in a database. And then there's raster, or imagery data. And our tool for analyzing vector data, also known as tabular data, is BigQuery. And then for imagery data, we have Earth Engine. So I'm going to start over here with BigQuery. So Matt already talked a little bit about the performance that you get out of BigQuery. That absolutely goes for BigQuery GIS also. So an example of that is the state of Texas. In the US, they had more than 12 million statewide parcels, and they wanted to understand how many of those parcels had impervious surfaces. And to do that, they ran this rather disgusting geospatial join, which is massive. Now, they ran that on a managed Postgres database, one of ours. So I show you here. It was a Postgres with PostGIS extension. I think it had 2 terabytes of SSD, 45 gigabytes of RAM. It's not a small machine. It was a well-spec'd machine. A query took 5 hours plus to run. Now, as a trial, they ported it over to BigQuery, didn't change anything, didn't change the code, didn't change the query, didn't change the data. That ran in 12 seconds. So you can see the sort of performance gains. You can go from just running analysis to actual interactive analysis just by moving your workloads to BigQuery. So a really interesting case study was with our customer Geotab. So Geotab is a fleet telematics company. They put devices in cars and they collect live GPS coordinates from vehicles all around the world. I don't know if we share the decks afterwards. But anyway, maybe I can share the link because we actually talked about this at Google Cloud Next, and a lot of our sessions are, let's say, on the fluffy side. This one's not. If you're really into GIS and you want to know a lot of technical detail, there's a really good session where they talked about this for about 40 minutes. But at a high level, so Geotab is a fleet telematics company. They stream in about 40 billion data points a day into BigQuery. And what they were doing with that is they wanted to provide a service to their customers to understand traffic at intersections so that they could make decisions like, okay, I want to add a turn lane, or I want to change the light timing. What sort of effect is that going to have on traffic? Because obviously idling traffic is a huge problem all around the world. It screws up your commute times, you spend way too long in your car, it's bad for the environment. So this is a high priority problem. So Geotab only has the data from their vehicles. So they have the GPS coordinates streaming in. And from that, they needed to figure out, okay, what are the intersections, first of all? So they took some OpenStreetMap data and did some fancy geospatial clustering, and they were able to figure out, okay, these are the intersections. And from there, these are actually the lanes. And then they wanted to know, okay, but how do all of those ways, so the turn lane and the straight lane and all these different ways, how do they connect together? And so they recursively connected all of the ways together. And then they did that for the entire world. That runs on BigQuery in 6 hours. I hope this is going to work. So we'll see. So BigQuery not only can store tremendous amounts of data, but as far as geospatial, when we're talking about making visualizations interesting, because data is no good without visualizations, and geospatial data especially is no good without visualizations. To render that effectively, we create tile sets, right? So like we do in Google Maps, you can zoom in and out on your data. I hope this is going to work. There we go. So here is a nauseating visualization of zooming in and out on 300 million building data sets. This is a partner of ours called Carto. They have a lot of geospatial extensions. They have one for BigQuery that allows you to create these tile sets, and it doesn't actually matter if it's 300 million points, a billion data points. It's the same experience. It's nearly flawless, zooming in and out on that data. I was going to run a demo, but of course, the demo gods hate me. And this morning, Carto's demo site was down. So I do have video. We'll see if this runs. No, we have no audio. Okay. So this is the marine cadastre data set. It shows all of the vehicles in the world. They all have GPS trackers on them. And this is a visualization of Carto zooming in and out all the way down to actually individual levels. You actually see there's some sort of weird circular pattern going on there. I don't know what's happening in New York because the vehicles are circling. I know that this one is something to do with biodiversity. This has, I think, 1.4 million data points in it. So again, you can see in real time how you can zoom in and out. Right, and then I know the next one is going to be the New York taxi data set. So this is actually a data set that's available in BigQuery. You can play with it for free if you'd like. This is a visualization of all of the taxi trips in New York. Right, so that was BigQuery, which is just one of the tools. So the other tool that I want to talk about is Earth Engine. Has anybody here heard of Earth Engine? No? Just a few people? Okay. So Earth Engine is my favorite. Earth Engine is a remote sensing scientific platform. This has actually been around for more than 10 years. But previously, we only made it available to not-for-profits and non-government organizations to do research. Just this year, in July, we decided to finally make it GA, which as a GeoSpatial person, I've been waiting for my entire time at Google. It's a pretty amazing platform. There's actually 3 components to it. The first is the data catalog. So if you're doing any sort of remote sensing work or you're looking at satellite imagery, you know that actually sourcing the imagery can be a real pain. We keep the data catalog up to date. So there are, it's nearly impossible to keep the slide up to date because we keep updating it so fast. There's more than 900 data sets in there now. There's more than 70 petabytes of data that's available. That data is available to use for free. You don't have to download it. We host all of that. We wear the cost for that. You pay for the compute only. We also have the computation platform. So this is a massively parallel, co-located data processing platform that allows you to scale out to the equivalent of thousands of computers. And there's actually an ecosystem around this as well, because it's been around for 10 plus years. There's a huge community of users. There's a Stack Exchange flow. There's YouTube channels, a million GitHub repositories, just a really collaborative ecosystem. And also in the neighborhood of 16,000 published research papers using Earth Engine. So the way that it works, I already talked about the data. I've talked about the computation as well. There's 2 APIs. There's a JavaScript and a Python API. In the console, what you get is the JavaScript API. You can use the Python API as well in a Jupyter Notebook. None of the computation is done locally. It just assembles a DAG and sends that off to the computational backend. So you can use either one, and they're feature parity. And it is browser-based completely. So when I demo this, more than I would like to admit, my children are at home and they're gaming. And I'm sitting there with my not-so-great internet connection. It's not a problem. It works just fine. You really and truly only need a modest internet connection. This is, managed services. They have a value proposition, and that is that we do all of the stuff that you don't want to bother with so that you can do the data science. An example of what you can do with Earth Engine. So this is a picture of the Isle of Mull in Scotland. This is a classic problem with remote sensing. There's clouds in this image. So difficult to actually see what's going on the ground. In Earth Engine, with one line of code, you can actually take a mosaic of pixels and remove the clouds and then return you the image underneath so that you go from clouds kind of useless to underlying imagery. That's one line of code. This is my favorite Earth Engine case study. So you're probably thinking, okay, that's a lot of talk. What are people doing with this in real life? Well, the European Commission Joint Research Center wanted to understand 3 decades of global surface water change. They want to do that in high definition. So this is obviously an environmental problem that's on a lot of people's minds. This had never been done before because the scale was actually impossible. So they used over 3 million Landsat images. It was nearly 2 petapixels of imagery data. They calculated that if they'd done it on a single computer, it would have taken 1,200 years. But that ran in 7 days. Oops, that's out of place. I do have benchmarks for what our performance with BigQuery looks like compared to other cloud data warehouses, but it's not supposed to look that in there. What has happened to these slides? This is a disaster.
Not guilty.
Wow. Okay, I think that's the end of mine.
Yeah, go on, I'll pick up.
There we go.
All right, thank you very much.
Sorry.
Okay, so I guess a couple of things to take away from that. Obviously, the scale and the compute power that we've now got access to that we've never had access to before. One of the other areas, and I'm conscious of time, so I'll be quick with this. One of the other areas that Google is really keen to move forward is this whole concept that machine learning should be for everybody, and it shouldn't just be the smart data scientists. Any smart data scientists in the room? Come on, own up, because I'm gonna badmouth you if you don't own up. I'm only kidding. At Google, we see machine learning being leveraged in all functions, whether it be the developers who are going from producing their applications in a traditional rule-based approach, if then else, etc., to actually looking at ways now to use machine learning and to use data to drive the capability in their application. So one example of this is Gmail. Any of you use Gmail? So you'll now see that it'll start to auto-complete your sentences as you type in. So you start typing and finish your sentence, you press return, you've saved yourself a fraction of a second. That adds up over time. So things like that, look, we're trying to enhance user experience and we're trying to bring ML into everybody's hands. Now, one of the examples here with BigQuery, just a stat, 7% of enterprises will use cloud-based AI infrastructure to operationalize. The challenge we've got with the data scientists are they're very skilled, they're very expensive. You're looking at 300,000 AUD at least for a very good data scientist. So the skills are scarce. And lots of complexity involved, and obviously then there's an issue about security when you've got data scientists taking data out of data warehouses and pushing it elsewhere. Because the traditional ML workflow would be something like this. You might have a data scientist who's looking at doing some customer segmentation and goes to the data warehouse, that's the source of customer, extract the data, put it onto my really high-powered machine, or even put it onto my virtual machine in the cloud, then do all my modeling stuff. And then where's your data governance gone? As soon as that data gets exported, you've got a risk from data exfiltration to sources that don't come under your governance process. What we can do with BigQuery is we've actually put the machine learning inside the warehouse. So it sits alongside the data. Now, this is useful for several reasons. Firstly, anyone that understands SQL can actually create models and run models to test their hypothesis. So if you're a business subject matter expert that understands the data and you think there's a correlation between these 3 attributes in the data and the outcome, you can create a model to test that. And it doesn't work, fine, throw it away, do another one, iterate around. But if it does work, then you can start thinking of passing that through to the very smart data scientists, and you've actually proven something before it goes there, and that means they're not wasting their time. A lot of the feature engineering can be done in your SQL statement. So you're preparing your features, you might be classifying your data, you might be cleaning up your data, all can be done with SQL in the database. So 2 steps, I'll just show you via this GIF. So you can create your model, you put the type of model that you want to run. This is just a standard linear regression based on the number of trips. And then once it's created, you can then use it, predict model with the same features, and it will give you an output predicted number of trips. Very, very simple and easy to use at the entry level. We've started to get more sophisticated with it, and Roadmap now is showing some really cool ML algorithms that we're implementing. In addition, you're able to import and export the models to use elsewhere. So obviously in a production environment, you wouldn't necessarily use SQL to determine what the next best action for a customer is. You want to export that into your web-based application to actually do that. And you've got the ability to do that via BigQuery. And the problem is solving now all of a sudden ML's in the hands of the business and data analysts to start that process, to start looking at the opportunity and then push a more qualified opportunity for the data to the smart data scientists who then can do all the operational stuff needed around it. So these are the currently supported models around classifications. We've got clustering algorithms in there. There's regression. There's MLOps, as I've mentioned, so you can import and export your TensorFlow models. We also have hyperparameter tuning for those smart data scientists in the room. And we're tightly integrated now with our AI ML platform, which is Vertex. Roadmap for coming. We're doing a lot more with time series. So those of you that are working in mining with OSI soft and with those other historians, one of the challenges in the mining space is you've got data where you'll get a series of data flowing through, then you'll have big gaps. With these features, all that gets handled automatically and the data gets extrapolated. So time series is one that I'm really looking forward to, and there's lots more. I've included the links in the pack if we share the pack with you. Finally, some use cases, and you'll all have come across these, no doubt. Churn prediction, audience segmentation. We do a lot of work with Spotify. How many of you use Spotify? You should be using YT Music, YouTube Music. No, I'm only joking. Spotify is awesome, and we do a lot of work with Spotify, and we've worked with them around personalization. Personalization is a big topic right now, and as a result of the work we did with them, they increased their subscriptions, the premium subscriptions, by 26%, just by giving better recommendations to consumers. So for those of you in that sort of consumer world, there's a lot you can do in this space. Some samples here by industry. So we're not only working with the retail sectors and financial services. We do a lot actually in mining as well, and oil and gas. In fact, that's my day job, is looking after those customers. A lot in the telemetry space, looking at how vehicles are being driven on mine sites, for example. You can do all that now, and having the power of BQ behind it lets you actually unlock more insights with the machine learning. This is just giving an idea of the roles. So if you're a data analyst or a business specialist, you can use BigQuery ML. If you're an ML developer, we do have an auto ML function, which you bring your data and apply our models. And then for the data scientists, then we've got TensorFlow, Vertex, and what you'd expect from a full data science platform. Some links here I'll share with you. And I was going to do a demo, but I won't do that given the time. We'll go straight to questions. We got time for questions?
Yep. Okay,
we'll go to questions. Thank you very much. Any questions? Yes.
Still an explainability side to it, because it's kind of like from an ethics point of view that you have. Thank you.
First question.
You're gonna get lots more questions.
I've only got a few. Go on, carry on. Sorry.
Yeah. So there is a thing, right, in this industry that you can deploy some best AI models, but are ethically sound, and there have been some controversies around it in the past where they were amazing ML models, and it was in the US as well that a judiciary system they were using an ML system which was racially biased, because people deployed those AI systems. They were really good, but they never knew how it actually worked. Do you see that sort of a problem with Google BigQuery?
Massive focus point for us is to have explainable AI and ML. We've got a suite of rules and regulations about how our AI ML should be used, and explainability is a key focus area. Do you want to say anything more on the explainability bit?
Explainability is now part of BigQuery ML. So you can actually get global explainability of your model, and you can also get single prediction level explainability. But as Matt said, this applies across the board for all of our ML products. So we use TensorBoard for custom models, and then actually the AutoML models that Matt was talking about, you can actually see for vision, like pixel specific. I cannot talk today. I'm sorry. But you understand what I mean. Like it will tell you specifically which pixels were involved in making the prediction. So yeah, huge focus area and also a huge area where we're trying to democratize that as well.
Other questions? Got more of these? Yes.
I don't know.
Okay.
Where I work, they still have a lot of the GeoJSON data on the SQL server. When is the point where they would actually move to like a more parallelized warehouse for geodata as opposed to like a single node?
So you can natively load GeoJSON straight into BigQuery. It's a format that we natively handle.
Yep.
Are you running, is it an Esri backend? Is that what
Yes.
SQL Server's for? Okay.
I'm not a Geo person, but yeah, I know it's
Okay.
ArcGIS at least.
So for the Esri nerds in the room, it is now supported. It's a supported configuration. You can't use BigQuery for the Arc SDE, which is the guts of it. You still have to use a Postgres or a SQL server. But for serving map layers, you can use BigQuery. And so we have customers that are doing that because of problems of scale.
Yeah.
So Esri is an amazing piece of software, but actually still kind of suffers from tightly bound storage and compute. So we have customers that offload those workloads into BigQuery, the ones that don't need to set in the Arc SDE.
Okay, cool. Thank you.
Yeah, so if your business is starting to talk to you and moaning about how long it takes to render the maps and things, then come and speak to us.
All right, so it's the mapping where they would eventually.
In that capability, yeah, and any of the mapping
analytics,
algorithms,
actually.
yeah. Question at the back?
Yeah, you mentioned a couple of times mining industry.
Yes.
Do you have any examples of the construction industry? I don't know, the rail project.
Yes.
Yes, we do. Do you want to go with that one?
Can we mention them by name? I think we can.
We're
All right, so we're working with a very large construction company that's initials are LL that is based in Sydney, but it's actually a global company. They are, all in. There's actually some public case studies. I should probably just say there's Lendlease. So absolutely in Australia and across the world.
And we're doing quite a bit in sustainability space with Lendlease. So how do we engineer for the houses of the future? What's the optimal configuration for your footprint of the area that you're building in terms of the sunlight and all that sort of stuff. Some really cool work that's happening in that space.
Some case studies are available somewhere online, you mentioned, or
Yes, if you go onto our website, you look for customer case studies, you can search by industry.
I'll add it to the deck if we're sharing the deck. Any final questions? Yeah.
how does Databricks play with BigQuery and all your models?
This is a question. I think you're
No, I didn't plant. I promise you, I did not plant.
That's Dataplex. He talks about it all the time.
So I'm actually 20% product manager for Dataplex. Work with the US team. Dataplex is great at providing you with the logical layer over the top of your physical assets. So if you're looking at building a data mesh, for example, you want to define your business domains, do that in Dataplex. You can even define your data products in Dataplex and then start to plug the assets in. So it's an area that I'm talking to right now. There's lots of enhancements being made in this space. We've merged it with our data catalog, and the idea behind that will be we will leverage the data and data catalog, the metadata, to start automating some of the data lifecycle management. So you'll see a really slick, hopefully this time next year, you'll see a real slick end-to-end solution from managing your physical assets, leveraging the power of a logical data layer.
I think there was one more question in the back.
A question about Google Earth. How do you guys manage different coordinate systems, specifically with raster data? So, like, for example, longitude, latitude, to like MGA coordinate systems. Question.
Sorry, I'm going to get ready for that. There you go.
Okay, so Google Earth, unfortunately, is no longer a supported product. So how we manage that data, I don't believe that we're keeping that up to date. Google Earth Engine, though, is a totally different story, and I'm happy to get into the specifics with you, but I'm gonna.
Sorry, I wasn't kicking you off the stage.
No,
I was
that's
getting
all
ready.
right. Thank you.
All right, round of applause. Thanks, guys.
Thank you so much. I knew next to nothing for BigQuery or GIS. Now I do. So thank you very much. And Adrian's next, and I've forgotten the title of your talk, so I'll pass it over to Adrian.
I forgot to
Yeah.
hang out within the last
So you
couple
can-
of hours. Let me just share my screen so it's last option. Yeah.
That's coming through now on the.
Yeah.
So cool.
Yep. All good.
All right, awesome. So we should be good. Yeah. Hi everyone. So for those who don't know, take the mic with me. Hey everyone. So for those who don't know me, my name is Adrian Tompkins. I'm a solution architect with Databricks. So what I've got today is a bit of an experiment. I've got no slides. I'm just going to go straight into a product demonstration, and we're going to build something out from end to end. So this is normally a workshop or a demo that would run for an hour. So we're going to try and compress it into about 30 minutes and see what happens. So it could go horribly wrong, could be great. We'll see. So I'll just stay here pretty much for most of the talk, hiding in the corner.
As another experiment, do you want questions as you go or questions at the end?
I'll ask questions as I go along. So I'll go through different bits and we can shout out questions or ask along. We'll just have some fun. So in this particular example, what we're going to do is we're going to pretend we're an energy company in Victoria and we have to manage infrastructure to predict power consumption. So ahead of time, it'd be nice to know how much power everyone's going to be using so we could manage our infrastructure accordingly. So this is the pipeline that we're going to build with Databricks. We're going to ingest some data to begin with, take it into the lakehouse architecture. We're going to process some tables inside there, get some nice clean data to work with. We're then going to go through some experimentation, data exploring, and then finally build a model that can predict power consumption. And then after that, we're going to productionize that model and we're going to show how we can use it in some reporting scenarios. So it's a full end-to-end process. So just to give a bit of context about who Databricks is, if you haven't heard about us before, is that we solve a problem in that most enterprises struggle with data. Normally in a big organization, you have different personas. So you have your data warehousing people, you have your data engineers, you have your data scientists, and then you have to do activities such as streaming on top of that. And trying to use all these different technologies and use the different technologies involved in each of these different pillars or different personas that you need to use inside the data architecture, it gets really messy. So you have to transform data, move data around, you have to move data between different systems. It can be quite hard to do. And having done this in the past as a data engineer, it's quite a painful experience. So this is what Databricks have essentially developed. We've developed something called the Lakehouse platform. So the Lakehouse platform is, let's take the best aspects of the data warehouse. Let's let a data warehouse operate on top of your data lake, and we'll call that the Lakehouse. So that, in a nutshell, that's exactly what it is. We run on top of all the major cloud providers. So we run on top of Azure, AWS, and GCP as well. So if you're using any of your cloud providers, you can use Databricks. So with that out of the way, we're going to get into this demonstration. We have a recommended pattern in terms of building data and data sets inside the Lakehouse, and that's to do the medallion architecture. So this is where we have bronze tables, which we ingest data from different sources and put it inside the Lakehouse. So that's your storage in your cloud environment. And we recommend putting that in something called the Delta format. So what Delta is, it's an open source storage format that lets you basically do your data warehousing operations. So it's ACID compliant. It has things like, so it has transaction history. It has the ability to roll back in time and see previous versions. It's got a lot of nice things that you don't normally get inside your traditional data lake sources such as Parquet, for example, or CSV or JSON. And it's very efficient and performant to use in the Databricks environment. So we're going to ingest some of this bronze data. We're then going to build some silver level tables with something called Delta Live tables, which is a technology that if you were at my last talk, I talked about a lot. And then lastly, we're going to use that in some feature engineering tables, some gold level tables. So this is our entire pipeline: ingest, build with DLT, develop some features, build a model, productionize the model, and surface some BI results. So to start off with, we're going to start with some data sets. We're going to pretend these came from some different source systems. In reality, this comes from a Git repo, but it's CSV data. So these are the data sets we're ingesting. So we've got 3 data sets sitting around in our lake, which we've extracted from our source systems. Normally, you could use technologies such as maybe Matillion or Fivetran or Azure Data Factory. There's a whole bunch of different tools that you could use to pull this data and extract it. So our journey is going to start with, let's say we've extracted that data and landed it somewhere already. So let's have a look at these different files. We've got a demand file, which is going to contain historic information about what the demand is in Victoria. We have a temperature file, which contains information about temperatures and daily temperature averages. And then lastly, we have a file which contains information about whether it's a public holiday or not on a certain day, which turns out to be quite an important factor in predicting power consumption. So coming down here, we're going to have a look at our demand data. We can see our raw data is pretty ugly. We have a date, we have a periods, which is this weird format, which is not great for anyone working with data. You'd rather have a date format or a date time format. And then we have an operational less industrial and industrial value. So these are the megawatt hours produced per half hour period on that day. So this is what that table represents. Not that great to look at this in its raw format. Coming down here, we're going to have a look at the temperature data, which again has this terrible date format, and we have the average temperature for the day. And then lastly, we have a public holiday data set, which just contains flat out the dates of the public holidays. Again, different date time format here, a bit more human readable, but we don't have a header on the column. So we've got 3 data sets quite messy that we now need to bring into our data lake and ingest. So any questions on that one? Are we all understand what we're doing? So to start off with, we're going to ingest this technology, ingest this data sets for a technology called autoloader and Delta Live tables. So this is what is going to bring the data into the lake. So here we have, I've already built these pipelines that's responsible for doing the initial ingestion. So what this is doing is this is going out to your cloud storage environment, incrementally bringing that data in and turning it into one of those bronze level tables. We then do some cleaning up and produce a silver level table. So this is the interface for Delta Live tables. It basically provides a really nice interface and environment to run your Spark code in or your Spark pipelines in. It simplifies the development because it handles all the dependencies for you. So it can automatically build out these lineage graphs for you to say, hey, these are these tables linked together. And it handles a lot of tasks as well for you automatically. So optimizing your tables, making sure they're up to date. You don't have to worry about that so much using Delta Live tables. So if you want to look at the actual notebook that powers it, this is what it is under the hood. So looking through, we have these commands to ingest that data we just looked at. We say we're reading a stream. So because we're reading a stream, we're doing incremental ingestion. So as new data comes in, we'll pick that up incrementally and land it in the lake in the Delta format. And we're not doing much at all here. We're just saying infer the types as best you can with order inferring types. And it's a CSV file, so do nothing. So this is our bronze table, just ingest it directly to Delta. We're doing something similar to the other tables that we got to, the other CSV files. So now we want to build our silver level tables. So these ones are the cleaner data sets that we want to feed into our model and start exploring on top of. So we can see here, we're doing some transformations on top of our data sets. So we're making the time look nice, and then we're converting some types around because the types can accrue across the stream.
Sorry,
And-
Adrian, can
yep.
we zoom in a bit for folks in the back?
Yeah, sure. How's that? Better? Yeah, so down here, we're basically providing some transformations, and notice we're not actually writing this data out anywhere. With DLT, you basically just specify what the logic of the table you want is, and then say, okay, DLT, you write the tables, you maintain the orchestration of that for me. I just want to write the logic. So I've written this in Python, but you could write this in SQL as well and just write these tables purely with SQL and have that built out for you. So now that we've done this part, we've ingested the data, it's gone running now without zooming. So I'll zoom out for a little bit here. So we build our tables. We can see the demand bronze table has this schema. See the demand silver table has built this. And now we've got tables, so we're going to do some exploring. So any questions on that one so far before we move on to exploring the data, seeing what's in those tables?
Sorry, Adrian,
Yep.
I have a question. How did you create the dependencies again? I think I missed that.
So these dependencies are automatically captured by Delta Live tables. So coming through here, see how I'm just reading the stream from the holiday bronze table? So what's going on here is it knows that this is part of the pipeline and goes, oh, okay, I'm going to have to build this table for this table, and that's the dependency. So that's how I can map out this lineage information and know the dependencies between these tables. So when this job itself runs, all these tables will be built all together. So it'll work out I can build these 3 tables in parallel with each other, and then I'll build these tables after this table. Or because this is a streaming scenario, it'll actually just make sure it has a definition of this table first, and then can start streaming data through into this table. So coming through to the next step, we're going to do some visualization and processing of that data inside a notebook. So first up, we just start using the database, so we don't have to qualify every time. And now we're going to do some selecting from it in SQL. So let's select from that bronze table. So this is the Delta table with the bronze level information. So this is the not very pretty information. We can see it's just got the date, the period, the temperature. It's also added this rescue data here, column here. So what this rescue data column is it'll recognize if something can't be ingested or maybe you have some corrupt data that lands. Instead of just breaking, it'll add that into the rescue data column so you can come back and repair it later on. So you can go back to this rescue data and rebuild your bronze table without going back to the source directly. So it's been quite fast to see what's going on and fix that up. So coming through here, we're going to look at our silver table, our temperature silver, and we can see this has now got the nice types associated. It's got a nice date time type, and we've got a temperature value. So now we're going to do some quick data visualization. We just do a select star from our demand silver table. Let's look at dates beyond 2012 and just go have a look at the data. And we can put a really quick visualization together and see what that looks like. So we can see throughout the period of a day, power consumption rises and falls. So that seems to follow a common pattern. And we can see there's some days where it's higher. There's a consistent number of days here where it's low. It starts going up high again. It looks like this data is following some quite common patterns. So that's probably going to be a great candidate for putting into a model, a machine learning model, if you can pick out patterns from there. So now what we're going to do is we're going to take those data sets we ingested inside the DLT and we're going to aggregate them together. So bring them together in one table. We could do this in DLT, but we're doing this as part of the notebook instead. So here we're going to create a view that basically joins those data sets together, that performs the aggregate, and now we have a table of date and energy consumption value for that particular date and time. I think this is at the half-hour interval, whether that day was a holiday or not, and we have an average temperature. And so that's our base table we'll be working on. So let's say we don't want to use SQL. Let's say we like using Python instead. And more than that, why don't we all use pandas? Because a lot of data scientists just love using pandas. A lot of engineers love using pandas too. Well, Spark fully support Databricks and Spark fully support pandas and Python as a first-class citizen. And in fact, you can just call something in your data frame. Where's the call here? It's a pandas API, which will then convert your data frame to a distributed pandas API. So you can just use pandas as you would normally, but it's operating on top of a distributed Spark system. So you don't even have to think about that it's actually Spark under the hood or a distributed system. You just use pandas as you expect. So from here, we're going to do a quick summarization of some data. So we're going to look at this table that we put together and just see what it looks like. So we've just got some real quick visualizations and numbers pulled out. Here it's gone and highlighted that we have a very large number of zeros for the is holiday column. That could be a cause for concern if we're looking through different data sets, but in our case, we just don't have that many public holidays. So coming through here, we have now got some code where we're going to do something a bit more complicated. We're going to do a more complex pivot of our data. So we're basically going to group by year and pivot by year, and we're going to visualize that. So this is some complicated code operating on top of that pandas data frame that we're now going to use to produce this visualization here. So this visualization is comparing energy consumption over a year for 3 different years. So this is what the raw data looks like in terms of that table, and here's what the visualization is for it. So we've done the years 2002, 2007, 2014, and again, you can see this follows very similar patterns over the course of a year, making it, again, great candidate for data science and putting a model on top. So this is what we're going to do now. We're going to finally take this data set and we're going to put it in something called a feature store. So in the data science world or modeling world, you would register a feature store as a table of shared features that data scientists can use to plug into their models. So basically like a library of data or a library of features that data scientists can take and use. And Databricks has inbuilt support for building a feature store. So this code here, we're going to take a data frame and we're going to register that into the feature store. So we're going to create a database called energy consumption daily. And we say, hey, here's your features. And we can select from it like it's a delta table because under the hood, it's just a delta table. So this is our new feature store table. And if we look inside the feature store registry, we can see that here's the feature table, here's what its features are, here's where it's being used inside different models. So we get some more of that lineage information going on to work out how it's being used. And we can add our own custom descriptions, our key value pairs. So we can add extra information around this feature store to help other data scientists discover new features, see what these features are and use them in their own models. So that brings us to the end of the feature processing and we're about to start the modeling section. So any questions on the data exploration or the visualization tooling before we move on to the next part?
I have a question.
Yeah.
Do feature store tables, delta tables, get catalogs in Unity?
There's going to be an integration between that. So they're planning to merge this as part of Unity Catalog to bring that in. So you'll end up having a cohesive experience in Unity Catalog for the data science side of things too. Yeah. This question. Yep.
I did my certification some time ago now, so I don't know, it's a bit mixed up. But there was this thing, right? Like there are, from what I remember, there are 3 pillars in Databricks. So one of them is the Databricks SQL, the other one is the data engineering, and the last one is about machine learning. Where are we at the moment? Are we at Databricks SQL side?
So we've been operating on the data engineering side of things, and with the creation of this feature store, we're starting to head towards more the data and machine learning approach. So yeah, it's a good question. So if you go down the side here, those covers those exact 3 personas that you're talking about. So in the data engineering persona, you have your access to the tools that are specific to a data engineer. In machine learning, the biggest change here is that it adds some extra options to the sidebar. So you'll get the option to see the feature registry. It might be open already in this tab. Yeah, so you'll get the options for experiments, feature stores, and models. So this brings a bit more in that would not normally be so relevant to a data engineer. And then the SQL persona, which we'll show to you at the end, is quite different experience. It's really geared towards analysts and treating SQL as a first-class citizen. And we start talking about data warehouses then. So yeah, that's a question. But yeah, we're definitely in data engineering now. We're just moving over towards machine learning.
Right. But and we are importing the data. Should it be in? Is it okay to be in data science and data engineering, or should it be in the Databricks SQL side of things? Like, would you say that there should be a like the responsibilities should be divided?
I would say either data science or engineering or machine learning would be the persona you would operate under. I mean, it could be either or for this because you both have the same sort of the same sort of tooling available to you. But the SQL persona is really just accessing, looking at existing data sets.
Just one more for me. Who typically owns the feature store in the business? Is it the data scientists or the data engineers?
I would say data scientists. I would give them the ability to own their own features and maintain that. Because when you have ownership of something, you tend to care about it, and they care about their own features. So I'd imagine we want to give them, basically, I think we should give them the tooling to be able to manage it themselves. And that way it reduces the time in that teams need to be able to build up these things. But it's definitely a interesting question, depending on how I run things. Yeah. Cool. All right, I might jump over to the modeling side of things. So just so everyone here is aware, I am a data engineer, not a data scientist, to make it clear. I'm not one of those smart people that we're talking about earlier on. So I've got no idea how this model actually works. I just wrap around it. And this so whenever I say, yeah, take it with a pinch of salt if I'm talking about the actual model, underlying model, but I can talk about everything around. So what we're going to do now is we're going to build a machine learning model that can predict our energy consumption based on temperature. So what we're going to be using in this technology is, in this tooling is MLflow. So MLflow is a tooling targeted towards data scientists that can handle a lot of things that they find quite important to them. So for example, experiment tracking. So when you're running experiments and doing experiments in Databricks, you'll track everything that happens. You'll track the metrics that the model performs to, you'll track the data sets that are being used, and that makes it very repeatable. So once you have a repeatable experiment, you can compare them with each other, you can select the best one, and then you have that, and then you can take that and package it up and turn it into a fully registered productionized model. So basically it's providing a nice tool set to do ML ops with. So you can go decide the model you want, put it in the tracking system with experiments, choose the best experiment, that becomes a fully fledged model, that goes into the registry, and then you can hand it over to the engineering team and go, okay, here it is in the registry, and then the engineers don't have to care at all about how the model works. It just sits inside MLflow and it's a registered model, and then they can take it from there. So it creates that nice separation of responsibility between data scientists needing to try and operationalize and productionize something. They don't have to worry so much about that. They just have to do what they do best, which is building a model that's quite smart, and they don't have to worry about the other side of things, which is the infrastructure, how to manage it, how to maintain it. So we get that nice separation. So coming through here, we are going to use the profit model, which is a forecasting model for time series-based data. So this is developed by Facebook, and apparently it's a great model for doing that. So coming through here, we are going to, has it gone? And let me reload the page because my nice graphs have gone, or maybe I'll have to change the view to back to 100%. in. I'm not sure if it's because I'm sharing my screen or something's going on. Oh, no, there we go. Okay. So what we're doing here is basically we're taking the feature set we just put in the feature store. We're kicking off an MLflow experiment, and we are going to train our profit model with the data that we just put in. And this is what is popped out of the model. The blue part here represents the actuals of what was actually done in terms of energy consumption. And the red represents what we're forecasting it to be. So we've taken some historic data, made some predictions. We've lopped off this bit of the data in the future, so we pretended we didn't know what it was and got it to do a prediction. And now we're comparing it to see how good it was. So you can see it's followed a general trend reasonably well, but it's missing out some peaks and spikes here. So now we've gone and logged this against the experiment, so we can refer to this experiment anytime in the future. We'll now do some more experimentation. We might change some parameters to this model. So we've chosen a slightly different variant of the model. And we can see it's done a slightly better job, but still not perfect. And lastly, we're going to build a better model, add some more addresses on there, and take into account some extra things. Maybe the previous count wasn't taking to the holidays into account, so we'll do that. And we can see it's gone and created quite a good representation now. We can see that it's actually predicting pretty well compared to the historic data. So chances are this is a good candidate model that we want to bring to production. But let's find the very best one. Let's do some hyper optimization and work out what the very best performing model is. So this is what we're going to use Spark for here. We're going to tell it to hyper optimize this model, which basically takes the model, retrains it across Spark's distributed system, so you can train hundreds or thousands of models in parallel and choose the very best one. And that's essentially what's going on here. So we're using a smart algorithm to train everything at once and work out what the best one is. And that's what we do. We pick out the very best one, and we put it inside the model registry. So this bit of code here says, let's get MLflow and then register that in, and we'll create the model. And that now sits along here. This is the energy forecasting model. So we have this model inside MLflow. So any questions on that before we move on to the next bit? All right, so this model now sits in the model registry, and we want to be able to use this model for inference. So we want to do something. Oh, sorry, question there.
I just want to ask, when you are training the models and register the models, where are we tracking the metrics, and do we have some thresholds that we sort of measure against before registering?
So in terms of where it's being tracked, I can show that inside the experiment window. And that should pop out to the actual experiment here. So inside here, you can basically get all the assets that went with the model, all the parameters that went with it, the different metrics that you wanted to track, so you can choose which metrics you want. Coming back up here, this should give you a grid view, so you can see a list of all the different models that you trained, and then you can select multiple models and you can start comparing them against each other. And so you can see how different metrics are performing. Again, I'm not the best end user of this particular product myself, but this is generally how you start comparing models, comparing between them, and just making sure that you've got the right one. Any more questions? All right, so now that we've got this model, we want to use it for inference. So one cool thing that you can do here is you can serve it as an API directly from Spark. So you can enable serverless real-time inference, and then you can just have this model sitting up and running, and then you can call it an API directly. But we're not going to do that here. We are going to do it as part of a data pipeline. So coming across to the deployment side of things, we're going to come through. We're going to take this, I'll zoom in again so we can see what we're doing. So we're going to pull this model out of MLflow, and we're going to realize, well, we need data to use it. We need to know what the temperature is going to be in advance to use our model. Otherwise, we can't do anything with it. So this is where we're going to take another model that sits inside Databricks. Another team has quite handily created this weather model for us that gives us weather predictions in the future. So perfect. So what we do is we take the model that's already registered, we pull that out, we get some predictions, 15 days in the future in Victoria. We build this data set, and now we have some data that we can use to predict our energy consumption. So we take this data set, we call model.predict, we put in the data that we just got, and then bam, out comes our prediction. So we have a date and then the predicted value. I'm guessing this is a range of upper and lower values around that prediction. So it's as simple as that in terms of creating a model. So what we could do as a data engineer now, we could run this as part of a data pipeline ourselves. We could run this as part of a schedule notebook. So you can create a schedule directly from here and say, hey, I want to deploy this as a job. You could go back and incorporate it in your DLT pipeline. So coming back to here, in DLT, you can get the model out during the DLT process and have it as another step in a DLT pipeline. So you can create a nice inference pipeline that way. Or you can use it in part of a notebook and you could write those results out to a Delta table here. So this is what we do here. We're just going to take that data and write it out to a table. And we have these tables of values. So in another example here, we show how we can do real-time streaming inside real-time streaming inference. So here we had a dummy data generator. I've selected some data from the dummy generator, and I basically kicked off a stream that constantly populated this dummy data. And then we have the model constantly making predictions as data comes in. So you can quickly build these nice end-to-end pipelines. If you want to use streaming, you can too, and it's very simple to do it. So you just pull the model out and just use it as a function, essentially. So lastly, we've got our data set here. Now we're going to jump over to the SQL persona and have a bit of a play with it in SQL. So any questions on the deployment side of things before we move on to look at this in SQL?
Is there any monitoring after you deployed it in terms of model drift?
Yeah, I think they have, as part of the serverless side of things, they're bringing in some model monitoring tools. I'm pretty sure we've got some accelerators as well to help with model monitoring. Yeah. I know it's a definite area that they're looking to invest in. There may already be tooling to help monitor as well built into the platform. So again, just because I'm not quite in the data engineering and data scientist side myself, I can't keep up with can't quite remember what we've got there. But yeah, we definitely, I know it's been a huge area of investment to look into. And there with the model, with the serverless side of things, that's where we're kind of bringing our model monitoring into that side of the stack. Yeah.
How do you manage model dependencies like libraries and so forth? Do you create container image, or is it requirements TXT?
Yeah, good question. So what we can do is you can, if you're using the inbuilt Databricks runtime, which I'll just grab my notebook for. So if you choose an ML runtime, so 11.2, for example, that comes with a whole lot of already available libraries that are packaged for you in that particular runtime. So that'll fix the versions of those ones for you. But otherwise, you can install your own libraries. You can use pip install, you can use library install to choose your libraries for your cluster. And then when you put that into MLflow, it'll log the dependencies and libraries that you're using to and the versions. So when you go and spin up an API endpoint, it knows how to, okay, I need to install these packages and have it up and running. Cool. All right, for the last bit, we're going to have a look at Databricks SQL. So this is switching over to our SQL persona, and we're going to see what some of this data looks like from a SQL interface. So here is our SQL interface. It'll be something very familiar to most analysts or SQL users. We can run some queries. So we're going to run the query and get some results out. We can do some plotting and graphing inside there. And we get tooling such as nice history of past execution. So you can go back and see what you've been running. So it's just a nice set of tools for querying and looking at your data from a SQL analyst point of view. So you notice when I'm running this, I'm connected to something we call a data warehouse. So in the other persona, we'll be using something called a cluster. So under the hood, they're really the same thing. It's just machines running and processing your data. But the warehouse view is a much more simplified way to spin up clusters. So if we have a look at the warehouse here, we can see a warehouse I've got here. It's a large, well, I've got to edit to show you. So I've made a demo warehouse. I've chosen it to be a large size. I mean, I think medium would suit most people's needs. But you can choose large, extra large, so t-shirt sizing, or a smaller warehouse. You can choose an auto stop period. So let's say after 10 minutes, I want to power this off automatically. And then if a query comes in, it'll spin up that warehouse automatically under the hood to say, okay, query's coming along. Let's spin up the warehouse and start executing it. And then you can set a horizontal scaling. So if you want to be able to handle more concurrent users, you can get the warehouse to scale up. So that's pretty much that. And then a great feature that we brought in with data warehousing is we've had SQL data, our serverless data warehouses too. So if I hit start here, what this is going to do, this is a serverless data warehouse, so I think, yep. and it's going to spin up a warehouse on our side of the fence rather than in your infrastructure. So basically, the startup time should be a lot faster than what you normally see. So that's running now and execute queries, and that's got spun up data warehouse on our side. So yeah, again, great thing to use, and that's eventually going to come to a notebook land as well. So you'll be able to have serverless notebooks. So that's something in the pipeline. But we're taking our SQL data set here. We've gone and selected some data. We're looking at the temperature data. So here's a table of what that data looks like, and here are some temperatures. And I think we've also, we've got the forecast data as well. So we're looking at some historic forecast, historic energy consumption data. And we can see in red here, we've got the forecast data. And that was just a really simple query that pulled through, and we used to use quick and easy visualization to see that. So again, nice, simple, quick, easy tools for data viz. We can then take those queries and we can build a dashboard out of it. So as an end user, maybe I want to build a nice dashboard, put our information together and serve it up to the rest of the business. Well, you can do that. You can do that directly from Databricks SQL. But if you have your preferred tooling, so if you've got Tableau or Power BI, you can connect to that directly through the connection details here. So you can use ODBC, so JDBC or ODBC to connect to the SQL endpoint and start executing queries immediately. So this is going to be quite nice if you want to access the data directly in your lake without pushing it out to another warehouse. You want to access it in Power BI, for example, with a serverless endpoint. You would just say, okay, Power BI goes in, makes a query against the warehouse spins up automatically in serverless, takes a couple of seconds. You can immediately be able to query the data in your lake, in the data lake, and you query that quite efficiently. So I think that's everything, the whole end-to-end process that I wanted to share. So is there any questions on anything we've seen today, SQL or otherwise?
I guess a question for me, no one has a question. Have you seen more people leaning towards using DBT with Databricks or DLT, which is what you just showed here? What's the preference?
Yeah, I don't think I've seen a bit of both, really. Some people seem to want to go native tooling and use DLT. A lot of people, I know Ash is a big fan of DBT. But yeah, no, we partner with a lot of different partners. So we're quite happy that we have a good partnership with DBT, and we want to help make that experience as good as possible. So it's up to you, whatever tool set you feel is best for you. I encourage using that. All right, well, I think I'll leave it there then. Thanks for doing this experiment with me. How was I for time in the end?
I think it was
Bang on, there we go.
Awesome.
Cool.
Well, that's it for tonight. There's probably still plenty of pizza left and plenty of beers and cider left, so please hang around to network until 7:30, and hope everyone has a great long weekend.